All right, so let's get started. So this is going to be your last lecture of physics. Okay, we'll be able to finish the topics today. So congratulations for 1 year of in physics. And I know it's a hard class for most of you guys. So yeah, I would say that's a kind of yeah, the final relief for you guys maybe. So um, if you have still have missing labs, you need to make up. There are 3 more sections that you can attend to make up your missing labs. Um, so I would suggest you guys do your best to make up your missing labs today, and if possible tomorrow. Okay, and then because then if you wait until Friday, then that's your last chance. Okay. All right. If your schedule allows you to make up your labs prior to Friday. Um, Also, the last homework it should be at homework number 11. I had a typo earlier, but it's a number 11 that's due on Monday. Okay, so because this will be our last lecture, then you will not get a, a reminder on that. Okay, so make sure you put that on your calendar before you forget. The final exam will be on Wednesday next week. It's a early time, 7:50, and then we'll meet in faculty 108. Okay, in the room that we had our exam 3. Also, the end of course survey will be due on Monday too. So if you get some time, you should finish that by that time. We'll see. We might have a few minutes left for today's lecture, so we can I can have you guys do that after if we are done with the lecture earlier today. Okay. All right. So um, so for today, we'll be looking into the wave aspect of light. Okay, so this is a wave optics. So you guys probably have experienced that if you have ever seen a CD, if you look at a certain angle, you'll see fringes, color fringes there. Or if you, when you were a kid, you probably you will probably like playing bubbles. You'll see that there's also colorful fringes on the surface of the bubbles too. Okay. So those are phenomena associated with the interference of light as a wave. So let's take a look on the some fundamental properties of wave. So light is a wave, so then we also would have frequency and wavelength for the light. Okay, so its speed in vacuum is equal to frequency times wavelength, which is equal to approximately 300 million meters per second. Okay. When light enters medium, then its speed will be reduced by the factor called index refraction m. So V then is equal to its speed in vacuum C divided by m. Okay. Now, when light enters the medium, its speed reduced. That's because its frequency actually reduced. Okay. Or actually, it's the wavelength is being reduced. So the frequencies will remain the same. Uh, Wavelength then is shorter than it's in the vacuum. So that's equal to lambda, also equal to lambda divided by m. Okay. Uh, a quick review on what we learned for waves. So if you have 2 waves meet in space, they will add up algebraically. So say if you have y1 and y2, when they meet, you just add y1 and y2 up to be a resultant wave. Okay. So in that case, if you have 2 identical waves meet in space, they will add up. We call it constructed interference. So for 2 waves to meet at a location, they might have traveled through different paths. So if that's the case, then 2 identical waves coming out of 2 identical sources meet at different locations will interfere with each other. Okay, so depending on their path difference, they might add up, they might cancel out, or they may just do in between, partially cancel out. Okay, so you can prove it mathematically, then the resultant will be again the y1 plus y2 for 2 waves. Okay, so if there's a path difference, what you will get is, so then if there's a path difference, for the argument in the sine function at the end, you'll have a difference of k times delta x compared to the original y1 or y2. Okay, so that's the difference. So it's resulting into a phase difference in the argument. So delta equal to k times k delta x. So k is 2 pi over lambda, which is called wave number. The path difference is delta x. So you're simply doing that x1 minus x2 or the other way around. Okay. So then the phase difference caused by path difference is equal to 2 pi over lambda times delta x. You can rearrange the terms. So here gives you delta x over lambda times 2 pi. Okay, for the phase difference due to path difference of the two waves. So if the path difference is equal to integer numbers of lambda, then you'll see the phase difference due to the path difference will be multiple of 2 pi's, which means the two waves will add up. Okay. On the other way around, if the path difference is half of lambdas, then the two waves will cancel out. That means destructive interference. Okay, so those are the conditions. That is two identical waves coming out of the two identical sources. The sources are in phase in that case. Okay, and if sources are out of phase, that means the sources are different by pi originally, then you have the conditions flipped. Okay, for construct interference and destruct interference. So light is also a wave, an electromagnetic wave. So then that will apply here. So if you have two light waves, okay, coming out of two slits, so you have originally the same light source hit on the two slits. Then out of two slits, you have two light coming out of those two slits. When it hits on the screen behind the two slits, then light wave coming out from the two slits will have path difference. Okay, so then they will interfere with each other. So you'll get bright fringes when the two light waves are differ by the path. The two light waves will have path difference of integer numbers of lambda. You'll get bright fringe. And if they are different by half of lambdas, you get dark fringes. Okay, so you'll see bright fringe, dark fringe there in the pattern behind the screen. Okay, and so this is a top view of this. If you have slits over here, if you have ray hits on here, then you'll see interference over there. Okay, so this is what happens on the screen. This is before it hits the screen. Okay, so you'll see that. If you are using red light here, then you'll see that. Okay. All right. So for two light waves coming out of two slits, when it hits at the same spot on the screen here, if we zoom in there to see if the two arrives at P at the same time, then the path difference for these two light waves, 1 and 2, will actually differ by only a small part of it. Okay, so then it will be this part. According to geometry, it will be d sine of theta. D will be the separation of the two slits. Theta will be the angle theta here. Okay, from the two slits to here makes with the horizontal theta. So in that case, delta x is equal to d sine theta. Okay, so then phase difference small delta is equal to d sine theta over lambda times 2 pi. Okay, if that phase difference is equal to integer multiples of 2 pi, then we have constructed interference. Then that means we'll be seeing bright fringes on the screen. Okay, when that happens, you can set the d sine theta over lambda times 2 pi, which is delta. Okay, in the previous slide, 2 equals to m times 2 pi. So 2 pi and 2 pi will cancel out. Then you'll have just d sine theta over lambda equal to m, which if you multiply both sides of the equation by lambda, you get d sine theta equal to m times pi. Okay, and m will be the nth order of interference maxima. So that means the if you are counting from the center fringe outward. Okay, so that's the number of the fringes you'll see. Okay, and then we denote this theta as theta sub m, that refers to the mth order different interference, the angle of it. Okay. On the other hand, if this phase difference due to path difference is equal to 2m plus 1 times pi, so that's basically half of 2 pi. Okay, so this is like 1/2 times 2 pi, and then 3/2 times 2 pi, etc. In that case, m again equal to 0, 1, 2, 3. You'll set this is the delta equal to, it should be also equal to that for the distraction interference condition. So set this up, this equal to that, the pi and pi will cancel out. Okay, and if you divide both sides by 2 and then multiply both sides by lambda, you get d sine theta equal to m plus 1/2 lambda. This is a condition for you to see the dark image, dark fringe on the screen. Okay, so that refers to m's order of interference minima. Okay. All right. So let's take a look on this example on the double slit interference. So it says two narrow slits separated by 1.20 millimeter are illuminated by light that has 600 nanometer wavelength, and interference pattern is viewed on a screen 2.5 meters away. And the interference pattern, it says calculate the number of bright fringes per centimeter on the screen in the region near the center fringe. Okay, so let's say this is your double slit, and then this is where your screen will be. This distance is 2.5 meters. Okay, let's say that's L. The two slits are separated by 1.2. Okay, so that's D is 1.2 millimeter, right? And they're looking for like 1 centimeters within the center fringe over here. So let's say this is 1 centimeter. This is y equal to 1 centimeter. Okay, so basically it's asking you how many bright fringes you will be seeing in this region on the screen. Okay, so how many are n equal to what? Okay, m equal to what? So you can be looking for the m's orders interference at y equal to 1. Okay, so that's the case there. This will be the theta sub m. Okay, so you can see from the geometry, you can calculate tangent of theta. Okay, that should be equal to 1.00 10 to the negative meters, because that's 1 centimeter divided by L, 2.5 meters. Okay, so this will be a small number. So that means you can use a small angle approximation if you need to use sine of theta. Okay, so sine theta equal to that, because this value is small. Okay. All right, so that means theta angle is the small angle. So you're looking for how many bright fringes you will be seeing within 1 centimeter. That means you are going to take a look on the equation for the interference maximum. So d sine theta m equal to m times lambda. And if you solve for your m, then that will tell you how many bright fringes will be within the 1 centimeter region. Okay. So m is equal to then d sine theta over lambda. Okay, you have d, you have lambda, and then you also have sine of theta, which you can use approximation of the tangent theta there. So this is approximately equal to d tangent of theta over lambda. and D is 1.2 millimeter times, that means 10 to the negative 3. Tangent of theta would be 1.00 times 10 to the negative 2 meters over 2.5 meters. Okay, divided by lambda. Lambda is given as 600 nanometer. So 600 times 10 to the negative 9 meters. Okay. All right. So with that, it gives you M, sorry, looking for M. So M is equal to 8. Okay. So that means you'll be seeing 8 bright fringes within that 1 centimeter range. Okay. All right. Any questions you guys might have on this? Okay. So if not, then we'll just move on to the next topic on single slit diffraction. Okay, so it turns out that if you only have one slit, single very small slit, if you have light shine on that slit, you'll also see fringes on the screen behind it. You will see dark fringe, bright fringes at the center, and then dark fringe, and then bright fringe, etc. in alternating pattern. Okay, so it behaves like 2 slits interference. However, here we only have 1 slit, so we just call it single slit diffraction. Because for a single slit, you can actually divide it into, or you can imagine that it could be divided into very small pieces. Then you have small slits over there, a number of slits, small slits there. Now, for each of the small slits, you can imagine there will be a light wave coming from out of that. Okay, so if you pick one here, some distance halfway of half of the length of this list, down here you can find another wave, light wave, that will go in that direction. So when these 2 light wave they hit on the screen, they actually will be traveling with different paths. Okay, so then there's a path difference from the 2 light waves there. You'll see then the path difference is again this the size, the length of this side times sine of theta. Okay, if this is 90-degree angle, although I don't think the figure shows in that way, but yeah, it looks like, yeah, nearly 90 on the screen. Okay, so in that case, then this is 1/2 of the opening size of the slit. So one half of A sine of theta. If when they hit on the screen, if you see the dark fringe, then that means the difference is 1/2 of lambda. Okay, for the first dark fringe you'll be seeing on the screen. Okay, and then 1/2 can cancel out. You can see then A sine theta 1 will be equal to lambda. Okay, so that's the first dark fringe you will be seeing. All right, for the second one, then you'll be doing 1/2 A sine theta 2 will be equal to 2 times 1/2 of lambda. So then that will be equal to 2 times of lambda. Okay, so A sine theta 2 will be equal to 2 times lambda, etc. Okay, now similarly, typically you'll have screen that is far away from the slits. For the distance of L compared to A, L is much bigger than A. So then Y1 is much smaller than L. Okay, so the angles involved here should be small angle. Okay, you can do small angle approximation if your angle is less than 15 degrees. Okay, so most of the cases you will see the angles are less than that. Okay, all right. So then in that case, for the discharge interference for a single slit, or for the to look for a dark fringe on the screen for a single slit interference, the condition would be A sine theta equal to M times lambda. Okay, where M is equal to 1, 2, 3, etc. So m could be equal to -1, and that just refers to you are at the other half of the screen, okay, from the center brightness, okay. All right. So we just derived this equation from the light wave, but it's one of the property of wave. So in that sense, for other waves, instead of light wave, you might have like X-rays or microwaves or radio waves hit on a single slit. You'll also be able to see the distract interference or construct interference certain distance after that, okay, for both cases, for both double slits and single slits, okay. We will take a look on an example that's not associated with light wave, but it's a microwave, it's still a wave, so then single slit condition will still apply here, okay. So this one says claim microwave are instant on a thin metal sheet that has a long narrow slit of with 5 centimeter in it. The microwave radiation strikes the sheet at normal instance. The first diffraction minimum is observed at angle equal to 37 degrees. So in this case, you don't necessarily will be able to use the small angle approximation because your angle is 37. But yeah, let's take a look on this one here. So this one says the opening of slit is 5, so that means your A is equal to 5 centimeter. It says your theta 1 for the first order diffraction minimum is 37 degree. Okay, so that will be theta 1. That means your m is equal to 1. So theta 1 is equal to 37 degrees. M is equal to 1. This is a diffraction minimum, so you'll be doing A sine theta m equal to m lambda, okay, where m is equal to 1. It's asking you what will be the wavelength of the microwave. So you're looking for lambda. Okay, so this is equal to 1, then lambda is equal to A sine theta. Okay, you have A, you have sine, you have theta. So it's kind of straightforward here. So A times sine of theta 1. It's 5 centimeters times sine of 37 degrees. Okay, that would be 3 centimeter. Okay, for your lambda in this case. Okay. All right. So that's single slit diffraction. Now let's take a look back on what we learned about wave also. So for waves, when we say two waves meet in space, if they have path difference, then there's interference. Um, Also, when we look at that for waves, we say if the originally two waves, when they meet, if they originally have a phase difference, okay, so that means in their sign arguments, the argument is already initially differ by a factor or phase difference of delta, okay, then when they meet, they will also interfere with each other. So if originally there's already a phase difference, okay, so then the two will add up, okay, and then you'll have a sine function, okay, with a new amplitude. So depending on that original phase difference, if that's 0, that means there's no difference, so the two will add up, that means construct interference. If the two has original phase difference of pi or 180 degrees, then they will cancel out, that means destruct interference, okay. So when light hits on the surface, sometimes you might see phase change of the light wave, sometimes you don't, okay. So to tell if you have a phase change when it hits the surface, so this is similar to when you have wave that is propagating from a thinner media to a thicker media. So you will have a phase change in the reflected wave when it hits the thicker media, okay? On the other hand, you don't have left phase change if you are propagating, your wave is propagating from a thicker media into a thinner media. So the reflected wave will not have left phase change, okay? So this is similarly for light wave. If light wave is traveling from a small index of refraction into a larger index of refraction median, then there will be a phase change of pi or 180. On the other hand, if your light travel from a larger index of refraction median into a smaller index of refraction median, then you will not have that phase change of pi or 180 degrees. Okay. So with that, we can take a look on this example. It says a film of oil that has an index of refraction of 1.45 rests on an optically flat piece of glass with an index of refraction of 1.60. When illuminated by white light at normal instance, the light of wavelength is 690. I think I went too far. Yes, this one we want to take a look. Sorry. For some reason, when I hit next, it went to the last page of the slides. Okay, so this is one we'll be actually looking at it for right now. It says light that has a wavelength of 500 nanometer is instanced normally on a film of water that is 1.00 micrometer thick. What's the wavelength of the light in the water? How many wavelengths are contained in the distance of 2 times the thickness of the film? And then C, the film has air on both sides. What's the phase difference between the wave reflected from the front surface and the wave reflected from the back surface in the region where the two reflected waves superpose? All right. So let's see. Pi is asking what's the wavelength of light in the water. So when the light enters the median, its wavelength will be reduced by the index of refraction. Okay, so let's call it lambda sub n. That means in the median, that should be equal to lambda in the vacuum divided by n. Okay, so it says 500 for the wavelength. So 500 nanometers divided by, for the water, it tells you the index of refraction, it will be 1.33, I think. It's not even here, but you can look it up for water. It's 1.33. Okay, so this is 1.33. Okay, it will be 375 nanometer. When the 500 nanometer light enters the water, its wavelength is reduced to 375. Okay. And for part B, it's asking you how many wavelengths are contained in the distance of 2t. So simply you'll be doing 2t divided by lambda n. Okay. So that will be the number of wavelengths. So 2 times 1.0 times 10 to the minus 6. It's 1.0 micrometer divided by 375 times 10 to the minus 9 meters. Okay. So that will give you 5.33. Okay. So it's 5.33 of the wavelengths will be contained in that thickness, 2 times of the thickness. Okay. C is asking you what's the phase difference from the two waves reflected from the front surface and then the back surface. So let's take a look on here. So let's say this is your thin film of water with a thickness of T, that is 1.0 micrometer. All right. Now, if you have the light wave hits here, so then if you are hit at normal direction, you will get reflected right back. Okay, so you can draw a reflected back light. I'm going to just shift it to the side a little bit, so we'll see those two will not sit on top of each other, but in reality they do. Okay, so this is reflected ray one from the front surface. Now, when light hits the surface of the thin film, part of it will be reflected, part of it will just enters the median. Okay, so that will go into the median, and then when it hits on the back surface here, partially it will reflect back upward. Okay, and then part of it will be entering this median on the other side. Okay, so you'll see these two reflected rays, 1 and 2. So these are reflected rays, 1 and 2. Okay, now let's see. So for the ray, those two rays, when they arrive at your eye, if you are looking at over here, then the two will enter your eye. Then you'll see the interference of the two reflected rays. Okay, so the phase difference of these two rays will be coming from two parts. Okay, so the phase difference, small delta t, is coming from two parts of it. So one is the path difference, will be delta x over lambda times 2 pi. That's the path difference. Now we are in the median, so that means we want to use lambda sub m here. Okay. And then the second part will be coming from if there's originally phase difference between the two. Okay, so originally they are the same coming in. For ray 1, you are going from n1, which is equal to pretty much 1. And then this is water is 1.33. So you are going from a thinner media to a thicker media. So your ray 1 will have a phase change of pi. Okay. For ray 2, it goes from water, and then the other side is air. So it's air again. So you're going from thicker medium to a thinner media. So this guy will not have a phase change. Okay, so that means that's 0. So if there's a phase change on ray 1, this is ray 1, this is ray 2. Okay, on ray 1 there's pi, on ray 2 there's 0. So the difference will be a pi. Okay, so this is from phase change of the two rays, two reflected rays. Okay, all right. So on this one here, this is this should be 2t, delta x should be 2t, because for the path difference for ray 2, it travel more distance than ray 1 by 2t, 2 times of thickness. So that would be that guy. Okay, so it'll be 2t over lambda m times 2 pi, which means 5.33, and then plus pi. Okay, so this would be 5.33 times 2 pi plus pi. Okay, that will give you 11.66 of pi. That to be the phase difference of the two rays, reflected rays. Okay. So again, when you are looking for two rays, you will be potentially considering the phase difference of the two, coming from 1, the path difference of the two rays, and then 2, the phase change of the two rays. Okay. If both of them have phase changes, then will be pi minus pi. That will cancel out. Then the net effect will be coming from just from the path difference. Okay. Any questions you guys might have? All right. So if not, then we'll take a look on the thin film interference. I think we had enough background on that. So when you see the colorful fringes on bubbles, that's because there's a thin film sitting on the bubble. Okay. So then when the light hit the surface of the thin film, um, the first ray that get reflected right off from the front surface will interference with the second ray that enters the thin film and get reflected from the second surface. Okay, so in that scenario, you might have you would have path difference from the two rays, and then you might also have the phase change from the two. Okay, so let's take a look on that. Let's see. Let's say this is a thin film that is sitting on say maybe on the water surface here in this case. All right. So, and then this is will be air in air. So when light instance on that, the first one for the refract ray, number one will hit here and then comes to your eye. Now part of it will enter the medium and then get reflected from on the second surface over here, get reflected back, and then hits the eyeball there. So depending on what will be the index refractions here, indices of refraction here of N1, N2, and N3. So if N1 is less than N2, then you are traveling from thinner media to a thicker media. Your ray 1 will have a phase change. Okay. Now, if N2 is less than N3, this ray 2 will also have a phase change. Okay. So then the effect of phase difference coming from phase change will cancel out because this will have a phase change of pi, and then this also will have phase change of pi. So the difference will be 0. So then the only contribution factor will be the path difference of 2t, okay, over lambda prime or lambda sub m. So lambda prime is the lambda sub m times 2 pi, okay. Now on the other scenario, if your N3 is less than N2, so if this is a thinner media, this is thicker media, then this guy will not have a phase change. Okay, that's the scenario we saw before. Okay, so depending on, be careful about like the index of refractions. Okay, when you take a look on different rays to determine if they will have a phase change or not. Okay, so taking account into both the path difference and phase differences, then we can take a look on the construct interference condition and then also destruct interference condition. Okay, so let's take a look on the construct interference here. So if for construct interference, then the condition will be phase difference will be equal to multiples of 2 pi. Okay, and in the case if you have only one ray that is having phase change, the other one does not have, so then the phase difference coming from the path difference plus the phase change, okay, of pi. Okay, and then if you have two reflected rays both have phase change, then the phase change effect will cancel out, so then you don't have plus pi there. Okay, so you should just set up then this equal to 2m pi or this equal to 2m pi. Okay, so depending on what you have, and then you can get the condition for contrast interference there. Okay. Sometimes you also see if you have two very clean glass slide, if you make a like small gap in between, say if you put a piece of like paper in between the two slides on one end, okay, then what happens here, if you zoom in, you can see For light instance on the first glass line, okay, will get refracted here and then hits this surface, get refracted ray 1, and then part of it will enter this air gap here, hits this surface, and then there will be ray 2. Okay, so the ray 1 and ray 2 will then have a path difference, and then on this one, ray 1 does not have a phase change, but ray 2 will have a phase change because ray 2 is from a thinner media to the thicker media. Okay, so then you also have the phase change effect. So at the end, you'll get interference of these two rays that will contribute into the construct interference pattern that you see for the two slides. Okay, glass slides. All right, so let's take a look on the last example here on the thin film interference here. So it says a thin film of oil that has index of refraction of 1.45 rests on optically flat piece of glass, which has index of refraction of 1.6. When illuminated by white light at normal condition, at normal instance, light of wavelengths 690 nanometer and 460 nanometer is predominant in the refracted light. Determine the thickness of the oil film. All right. So let's take a look here. In this case, let's see, it says there's a oil film. So let's say this is the oil film, thin film, sitting on top of a glass. So this is glass. Okay. And then on top of the oil, that's air on top. So for index of refraction for air, N1, that's 1. It says for oil is 1.45. And then it says for the glass is 1.6. All right. So if you have a light wave hits on here, it says on normal instance, but I'm going to just tilt it a little bit so you can see the refracted rays a little bit better. Okay, so it will get reflected. This is ray 1, and then part of it will enter this film and then get reflected back. So this will be your ray 2, ray number 2. Okay, so your ray 1 goes from N1, which is smaller than N2. So ray 1 will have a phase change. It will have a phase change of pi. So let's say plus pi. Your ray 2 goes from oil, and then this part of it will enter the glass layer. So it's glass layer. So N2 is less than N3 again. So then your ray 2 will also have a phase change of plus pi. Okay. So both have phase change of pi. So those two will cancel out. Okay. Then the overall phase difference of ray 1 and ray 2 delta will be coming from the path difference of 1 and 2, so it will be 2t divided by lambda m times 2 pi, okay? Plus pi minus pi, because one has pi, the other one has also pi phase change, so then they cancel out, basically. So again, this part is due to path difference. And then this part is due to phase change of the two rays, two reflected rays, okay? So that go away. So you only have to focus on this guy here, path difference part, okay? So this is 2 times of thickness, yeah, divide by that. So delta is equal to 2, let me see, for lambda m is equal to lambda over n. So we can rewrite that. So 2t over lambda divided by n, okay, times 2 pi. So then this will become 2 times 2 will be 4. Okay, so 4. Now let me just leave 2 pi there. So this will be 2 times n times t over lambda, okay, times 2 pi for the phase difference of the two rays. Now it tells us there are two light waves. They are predominant. That means they are constructed interference. So that means we'll set the phase difference of the two rays equal to 2 times m times pi. Okay, or you can say m times 2 pi, either way. So if you have multiple integer numbers, not integer multiples of 2 pi, you'll get construct interference. Okay, so this will equal to that to get the construct interference. Okay, 2nt over lambda times 2 pi then equals to m times 2 pi. Okay, so 2 pi and 2 pi would cancel out. Okay, so then you will have 2nt over lambda equal to m. In this case, n should be equal to the n2 because that's the thin film. That's where the path difference is from. Okay, so that's just write n2 here and n2 there. So this will be n2, 2 times n2 t. Okay, so this is for construction interference or predominant colors that you are seeing from the interference. Okay, so it says that these two wavelengths, 690 and 460. Okay, so then you can apply this condition to both light wavelengths, 690 and then the 461. So 2 times n2 times t over lambda equals to m. You can apply it to 690 nanometer of lambda. And then you can also apply it to 460 nanometer wavelength lambda. Okay. So if you put lambda as 690, it will give you 2n2 times t divided by 690 nanometer equals to m. Okay. So that's referring to m's order of interference. Now, this is applying to 690, and then you apply this to condition to the 460. So 2 times n2 times t over 460 nanometer. This would be equal to, so because this is a longer wavelength, and if it has the order as m's order, then this guy will have the order as m plus 1 order, okay? Because this is a lower wavelength, okay? So then you have those two equations, all right? The m is 1.45, so this is 1.45. That's given. N2 is 1.45. So you can see in the two equations you have two unknowns. You can solve for them, okay? By using the two equations, you can substitute, say, substitution of m here with this guy, then you'll be able to solve for your t, okay? For a few steps of algebra there, okay? I'm going to do a trick here to solve m and t. So I'm going to do 1 divided by 2, equation 1 divided by equation 2. That means I'm doing the left-hand side of equation 1 over left-hand side equation 2. That equals to left-hand side equation, or right-hand side equation 1 over right-hand side equation 2, okay? 2 times 1.45t is the same, so that will cancel out. So that means I would only have 1 over 690 nanometers divided by 1 over 460 nanometers, okay? That equals to m divided by m plus 1, okay? Now on this side, I can rearrange the terms. This is the denominator. In the denominator, it will go up. Okay, so then it becomes 460 nanometers over 600 nanometers equals to m divided by m plus 1. All right. Now, if we look carefully, you will realize that this is equals to 230 multiplied by 2, and then this is 230 multiplied by 3. Okay. So then it tells you 2 over 3 is equal to m over m plus 1. Okay. So then you can see then your m will be equal to 2, right? M equal to 2, and then this is 3. Okay. So once you have m equal to 2, you can put m back into equation 1 or 2 to solve for your t. Okay, so let's put back into equation 1. We'll have 2 times 1.45 times t over 690 nanometers equal to 2. Okay, so then your t will be equal to 2 times 690 nanometers divided by 2 times 1.45. Okay, that's going to be 476 nanometers. Okay. Questions you guys might have on this? All right, if not, then I think that's it for the lecture part. So we still have a few minutes. You guys can work on the end of course survey, okay? And I saw a couple of you guys have done that. So if you have done that, you are free to leave. So also for Friday and Monday's lecture, because we are done with lectures, so you guys can use those times for to prepare for the finals, okay?